Hello everyone. We hope you had a chance to listen to the first lecture and you got to try out the simple lab tasks with the overt. If anyone is still struggling with the overt access, please let us know. Please send us an email and we will investigate that. You need to be fully set up on the system so we can, so that you can try out the lab sheets. Just to recap, the first set of lecture slides covered the outline principles of cloud platforms. We briefly looked into the paradigms of cloud computing, namely infrastructure as a service, software as a service, and platform as a service. Those are the main ones. I also gave you some simple examples of what each of those mean. We also discussed the assessment for this module. And again, if anyone has questions about the assessments, please let us know either in a face-to-face session or via those online seminars. So in this lecture, we are going to look at the evolution of distributed computer systems. We will look at what distributed systems are. It's also important to understand how we got here to the era of cloud computing. While we can appreciate that cloud computing is a set of cutting-edge technologies and advanced principles, we need to acknowledge that it is the result of evolution in computing. And to be more specific, it is the evolution in distributed systems. Uh, in general, computing has evolved over decades and recently it has been growing rapidly. The cloud computing is, if you think about it, it's a mix of computing technologies that have evolved over time. So it's a lot has happened in the last few decades, and it's that evolution which has created the cloud computing paradigm. Now, I can give you an example. So so virtualization, if you look at it, so for example, virtualization is not something new. It has existed for IT specialists, so we know what computing is. It's pretty straightforward for us. But however, depending on what your expertise is, there are different ways to provision for computing. Some of us who think of ourselves as systems engineers would be putting hardware and software together. Others might just view computing as data processing with some IT tools. Smart systems engineers and robotics engineers see computing as making systems intelligent. Others who are networking specialists see computing as communication technologies. Who, for example, program systems for improving end-to-end data streaming. The thing with cloud computing is it allows for all of that. It provides for all of that, no matter how complex a system is, no matter how complex a software that needs developing is. So that's why we are studying cloud computing, because it gives you immense power irrespective of what kind of application or what you want to do in terms of your computing requirement. Oh, yeah, sorry, I missed the last one. So yeah, so creating and using communications and entertainment media, and a lot more, of course. So um, it just makes sense to look at modern computing like a utility. When we access resources on the cloud, it's a subscription-based network, subscription-based model. Just like you access electricity, water, and gas, the same way you can access computing power too. So you pay a fees or a tariff, if you like, and you get a service. Computing can be seen as a commodity and is delivered like traditional utilities. So what is utility computing? Utility computing offers computing as a metered service. So like our electricity or water, which is metered. Similarly, computing itself can be metered. It can be, we can have a subscription-based model which is charged based on your usage. So it provides a basic level of computing. The end user is not concerned about where the service is hosted or how they are delivered. Just as in our households, we are not really concerned about where your electricity comes from. Of course, you subscribe to a company, yes, but how it gets delivered to your home is it's not our concern. So similarly, cloud computing or computing in general can be based on those principles. So computing power can be delivered to users on a subscription based model, and then it could be metered, it could have a set tariff against it. So yes. So to give an example, one of the common things we mention about cloud is the content delivery network. So what we call as the CDNs, content delivery network. So the content delivery network are distributed across the globe. Of course, if you think about say Netflix or any streaming service, it is based on a content delivery network which is distributed across the globe. So the CDN, the content delivery network, provides you a service, say movies on demand, etc. But the user here himself doesn't have to be concerned about where the media is being streamed from, right? So he's subscribing to the streaming service, but he doesn't have to think about how it is being streamed or where it is being streamed from. So the user can access content without having to worry about the actual physical location of where the server is. So that's what utility computing is. Let us for a moment think about how far we have come. I mean, if you look at the slide, you can kind of you can imagine how what a quantum leap the computing has gone through. So those are the codes from many decades ago, from prominent figures from the history of computing, and they had predicted that computing will become a utility. I mean, that was many decades ago. They predicted at that time that computing will become a utility. What they've said is 100% true. If you look at the second quote there, what I feel is also significant is how John comments that it will become the basis on new and important industry. So they're saying that utility computing is going to be a part of a massive industry. Uh, at that time, they didn't know what that industry was or how it's going to influence it. All they knew that was it's going to be significant. But today, we are in the position to truly appreciate the scale of the changes or the influence of utility computing or cloud computing or fog computing, whatever you want to call it. So it's got a massive impact on the industry. So I'm not sure how many of you have heard about the fourth industrial revolution. They call it as the Industry 4.0. We had the third industrial revolution, and now we are going through the fourth industrial revolution. The Industry 4.0, as they call it, is dominated by technologies that are reliant on cloud computing, artificial intelligence, smart systems, IoT, etc. etc. So it puts into context the nature of utility computing and its significance to economic growth. So there are different paradigms that evolved over time, and many of which have made their way into modern cloud. And it won't stop there. It won't stop here. And it's like I said before, the computing is ever evolving. Things might be different in a decade's time. So a few years down the lane, there might be something even bigger. Once we tap the full potential of the cloud, or the full potential of utility computing. With each of these paradigms which you see there on your slide, we are dealing with various attributes or properties. Accessibility is about making the services of the platform available to users. Manageability is about maintaining the resources, both hardware and software, and managing the link between them. You will learn about managing the cloud resources when you study more about specific cloud architectures. Autonomic, in simple terms, means automatic and making the systems self-managing to an extent. Well, of course, I mean, it goes without saying, isn't it? I mean, because when you are subscribing to a cloud service, you shouldn't be bothered about its management. You subscribe to the service, and it should be available to you without you having to worry about what happens behind the scenes. So it should be autonomous. It should be automatic when it comes to managing the cloud resources. So for example, deciding on when to migrate to a virtual machine. Performance is about computational efficiency within the cloud environment, and scalability is about extending the services or the cloud platform and its resources. And we have the availability, which means just that it should be available. It's availability of resources, so users should be able to access resources whenever they demand to do so. And we have the quality of service. It's said as QoS, quality of service, is the quality of service to the end users. And we have SLA, service level agreements, which govern the parameters of service provided to users. Obviously, you're entering a contract with the service provider, so you are bound by the service level agreements. And there are many more. I think it will become a lot more clear as we venture deeper into the module. Now then, that is the bit of history. So you may or may not want to go through this. I will not go into this. I will not go into this at all. So if you fancy some bedtime reading, then the key milestones are in the on your slide. So this talks about the evolution of computing systems. You might already recognize some of the terms there, like ENIAC or the ARPANET mainframe. So have a quick read when you get the chance. So this slide helps us to visualize how things have evolved over time. It's the computer's food chain. It shows the hierarchy. It's the hierarchy of how computing evolved. So yeah. So the main, if you look at it, the mainframe contributed to the modern PC. As computers got more powerful, they got smaller, and I think they get smaller by the day, don't they? With distributed computing, the computing resources are scattered. So again, you can see the visual there. So the resources are scattered. They are distributed. Cloud computing uses some principles associated with distributed computing. For example, dividing up of tasks and processing them independently is a part of cloud computing. So cloud computing does make sure that when there is a big computational problem, it's broken down into smaller chunks, and that's how distributed systems work. So like I said before, once you boil it down, cloud computing uses resources that are across multiple data centers and servers, and that's why we say cloud computing resembles a distributed system. That's the principles are there within cloud computing. So how do you define distributed computing? Several computers share the workload and work collectively towards a common goal. That's what it means. So when a workload is chopped up and distributed across various computational units, that's what distributed computing means. The resources needed could be distributed across multiple systems and across multiple geographic locations. So what you got to understand is there is no such thing called a single unit here. So the distributed computing, always there's a group of machines, a group of computation units which work collectively. It's like a corporation. So they work collectively towards a goal. The goal being solving the problem, but it could be quite a significant problem. It could be a big chunk of a problem. So it needs to be broken down, and it's allocated to different machines, and they collectively work towards solving that computational problem. Having said that it's a distributed system, even a data center is classed as a distributed system. And when you think about a data center, what do you see? I mean, you walk into a room and then you see this massive rack of servers. There's a huge data center. They're all confined to a single geographical location. So let's say you walk into a data center, you see all those machines. They're confined to a single geographical location, but still they're classed as a distributed system because each of those data centers you see has got other distributed machines within that system which work collectively. So although it is confined to a single geographical location, data centers can still be classed as distributed systems. So why do we need distributed systems and cloud systems? Sorry. So why do we need distributed systems and cloud systems? The simple answer is demand for computing power. The computational problems faced these days require immense computing power. Obviously our office computers or personal computing devices may not have the processing power or the speed to crunch those problems. If you take a look at some of the modern applications like data mining, aerospace, engineering, and simulation, etc., etc., they handle large data sets, and in many cases they need to be processed in real time. So there's no way your laptop or your home computer is going to be able to manage that. So what the ideal situation, the ideal thing to do would be for you to subscribe to a more powerful service provider with adequate computing resources, and then you use their resources, and you solve the problem. So because there's a demand for computing power, with being all this sophisticated technologies and huge data sets, it makes sense to you know to subscribe to a cloud provider. So we acknowledge that modern computing is mainly down to computational power. So we can use something that there are different ways of achieving. When we say increase the computational power, that there are so many ways of doing that. So we can use faster hardware, for example. But there's more to increasing computational power than just adding hardware. How about increasing the efficiency of applications? What that means is, I mean, is there any way you can make your programs better? Can we optimize algorithms? So think about that. So it's not just about the hardware; it's also about making it suitable for making your program suitable for faster processing. Can we divide the task within your program into smaller chunks and get them processed by a distributed system? What do you think of that? If you're using multiple computers, each computer can work towards its task and contribute to solving a larger problem with more efficiency and speed than using a single computer to do the same task. So, like I said, there is no maybe there's no one correct answer to this. When someone asks you how do you improve computational efficiency, yeah, you can obviously add to the hardware, or you can optimize your programs. You can build multi-threading architectures, etc., etc. So it is not, there's no single solution to this, but there's no single no rule of thumb to make applications run faster. But there are quite a mix you can use to make them efficient. Yes. The architecture we have today is significantly different than what it was a few decades ago, and I think you guys got to appreciate that. I mean, yeah, so think about how far we have come. Again, going back to the history lesson. Um, but I mean, the way we deal with the way we expand our computing resources has changed. They had the scaling up model where systems are made more powerful by creating um, faster and more efficient processors. So that's a scaling up model. So systems were made more powerful by creating faster and more efficient processors. But we also have the scale out model, the scale out model, which were built using loosely coupled components or workstations. When you expand that model and marry different distributed systems together, you get low cost commodity supercomputing. So you got to clearly understand the differences between scale up model and scale out model. Because the scale out model is what's happening, what happened recently. Um, so they coupled it with the different distributed components and you get, what we have is a situation where you are able to get low cost commodity supercomputing. So this diagram here, this slide here, shows the differences between scaling up versus scaling out. You can see how the processing power can be increased by just adding more machines to the cluster. Well, in the previous slide, I mentioned the word cluster. I just remembered we just mentioned the word cluster. So what is a cluster? It is a parallel and distributed system which contains a collection of standalone machines. And although they are standalone machines, they work as one integrated machine. So what we say is, from an end user's point of view, it looks like a single machine, but in reality, it's a cluster which contains of numerous smaller machines which are capable of parallel and distributed computing. So when we say parallel, we mean each of these computers are able to process instructions or rather instruction sets simultaneously and independently of other machines. So when a problem is given to a distributed system or a cluster, it gets broken down into different smaller threads or smaller processes. They get allocated to different machines. Each machine works towards completion of its own task, and together, if you look at it from a broader perspective, together they're working collectively. Although individually they have got their own work as well. So that's how you got to imagine a cluster. So a cluster is a collection of nodes, and that's what we have established now. It's a collection of nodes. A node could be a single or a multi-processor system. Of course, it'll have its own input-output, memory, and operating system. Yeah, these are connected via a LAN or a local area network. Although a cluster is a set of machines, as I told you before, although it looks like it is a set of machines, to an end user, it appears as a single machine. If you think about it, this is how the cloud looks like from a user's point of view. So you as a cloud user will subscribe to Amazon, the AWS or Azure, whichever cloud provider it is. To you as a user, it looks like a single machine. So it's out there somewhere, and it looks like a single point of view. So that's what it is. So it looks like one entity, although in reality it's a distributed system. The end user often does not get the choice of which cluster to use. So when you subscribe to a cloud provider, you don't often get the choice as to which cluster to use. That's all intrinsic. So if it's all managed internally, there is a management. There are management algorithms which take care of that. But that's not something you have to worry about. That's not something you have control of. So yeah. So you can't choose which cluster your data gets processed in. That's not for you to say. We have already explained what parallel processing is. It is where many calculations are carried out simultaneously by dividing them into smaller chunks. So for the programmers out there, among the audience, many of you already know about the multi-threading architectures, multi-processing architectures. So you probably can contextualize this. So while you write a program, you can make your program suitable for parallel processing. That is by exploiting the programming efficiency. So to fully capitalize on parallel programming, you can probably write your algorithms which are more oriented towards parallel processing and multiprocessing. So yeah, you can incorporate that through your programs itself. The advantages are that it's cost efficient, it provides high performance and improves utilization of resources. So instead of having a monolithic software or a program, you can just break it down to enable parallel processing. Oops, which slide was that? There we go. So let's now talk about how parallel processing, how parallel processes communicate in a distributed environment. So let's begin put things into perspective. So what we're talking about here is there are different processes working in parallel. The different processes, it's a part of a distributed environment working in parallel. Now the question is, how do these processes communicate with each other? How do these processes communicate with each other in a distributed environment? Now, one of the simplest ways would be to have a shared memory where processes, so I mean processes, not processors. They sound the same. So processes. So processes is a task. So where so one of the ways we can do this is by having a shared memory where processes can set values which are intended for communication. So the memory is constantly read. So what's up? There's a common pool of memory where different processes, different chunks of programs write into this shared memory. So this shared memory will be the basis of the communication. So what happens is each of the process uh, looks at this memory pool, and that memory is used to transfer valuable information from one process to another process. So um, so what we're going to understand is any change in the values within the shared memory is a message. So this is what the message is. The message is if one process wants to send a message to another process, it just writes something into the shared memory, which is then accessed by a different process, and that enables the communication. The other method would be for each process to maintain its own memory, but in order to exchange messages or data, so each process must query one or more processors to coordinate the communication. So what could happen is one process could talk to the processor and say, look, I need to talk to this other process. Can you enable it? Right? So one process could directly communicate with another process, and that itself could be the medium of communication. So yes, this relies on distributed memory, and that's what message passing interface means. So that's the MPIs, the message passing interface, is enabled in a distributed environment for different processes to communicate with each other. So then we are moving on into grid computing. So it's pretty straightforward because like I said, I mean all of this technologies with distributed computing, grid computing, cloud computing, cluster computing, they're all linked with each other. So they're similar principles, different contexts, slightly different features. So yeah, in grid computing, this is a category of distributed infrastructure where there is cooperation among various institutions to pool their computational resources. So let's say that Leeds Beckett wanted to collaborate or rather cooperate with another university or a set of universities. So what they could then do is they could pool their IT resources, they could pool their computational resources. So that way there is this strong bond of cooperation between different institutions. And also the thing about this is that there is no heavy investment. I mean you can share your resources with others and they will do the same as well. So together you end up with massive amounts of computational resources for problem solving. So this coordination and cooperation helps with provisioning of computational power. So instead of you deploying your own in-house massive data centers and etc., it would be more fruitful if you collaborate with other institutions, and then you get access to their resources as well, and they get access to your resources. So within a grid environment, it comprises of virtual organizations. There are so many virtual organizations which form a part of the grid. So they kind of enter a contract on what they should on what should be shared and how it should be shared. In a virtual organization, they can choose how their resources is pooled into the grid environment. Obviously, because different organizations own different resources, they are heterogeneous. Also, these resources can be geographically distributed. They could be spread across the globe. So let's say that or rather we, in Leeds Beckett, want to form a cooperation with some institutions, some universities in Europe. Their data centers will be based in Europe. Our data center will be based in UK. So they can be geographically spread across the globe. But nevertheless, together they form a computational grid. So they form a computational grid. So it is like an agreement. It's a private setup between different virtual organizations, and it's not accessible to outsiders. And finally, we get to cloud computing, which I said before has been built on principles drawn from various advancements in networking technologies. It allows for ubiquitous on-demand access to shared pools of centralized resources. The cloud is aimed at service delivery over the internet, so we don't expect that the end user has got anything special. All they need is a good internet connection which is appropriate to the service they are accessing. That's all they need. A good laptop or a good computer with some standard internet access, that should be more than sufficient for them to access the cloud and do the and get the computational power they need for their IT requirements. Oops, I skipped a few slides there. Sorry about that. So you can now see how cloud computing architectures came into existence, and the diagram that shows the evolution from 1990s to 2009 and beyond till date really. It has truly revolutionized computing. There's nothing else to say about that slide, but it just shows that steep climb in the evolution of computing. Now this slide talks about the differences between traditional approaches like, for example, on-site services and hosted services versus cloud computing. There are some disadvantages of the traditional approaches. So if you look at the slide again, so you have the on-site servers. The on-site that used to be the typical approach. So when some company or some institution wanted some computing power, what they used to do is keep on deploying on-site premises, on-premises servers. So if your boss says we need more computational power, if you are the IT manager, what you will do is you'll go out and procure some servers. You install them on your premises, right? So it's got its disadvantages. One of the thing is the main upfront costs. It costs tremendously to invest that much on a set of servers. But if you look at the typical IT budget, look at on the right hand side, you can see the typical IT budget. So software 35%, hardware 60%, and there are other 5% expenses as well. But the percentage of total server utilization is about 6%. Now that surely can't be right. I mean that surely can't be efficient, right? So you invest all this amount and only 6% of the server is utilized. So that it's the ever growing expenditure to maintain on-site servers, on-site IT equipment. So it's really not feasible to do that. So it's just a waste of money to invest in detailed on-site resources. So therefore, I mean, I think it's a no-brainer really. The cloud computing provides a cheaper alternative, right? At the same time, you don't have to you won't have your servers collecting dust. Yeah, all you need is simple end systems which can connect to the server, and then off you go. So now we can appreciate the principles of cloud computing. Now, as said before, the resources are pooled to give greater computing power. Because it's a pay-as-you-go model, everything you do is on-demand self-service. In other words, the user decides which resources they need. Guys, you got to think, there's no such thing called as one size fits all in this, right? Um, so that's why there's a different pricing scheme depending on what kind of a virtual machine you need, what resources you need. So there are different pricing schemes. So it's not like that when you subscribe to the cloud service provider, you get everything. No, you don't. When you subscribe to the cloud provider, you got to go through this process of selecting what resources you need, and you pay the appropriate tariffs for that. So there is no such thing called as one size fits all. What works for you may not work for other people, right? Um, so yes, you got to understand that. So it's a purely subscription based model, and you got to choose what you need. It's just like I know it's just like picking pick and mix. So you got to choose what you need. Yeah, with the cloud environment, there is also broad network access. The services the user needs can be extended, and more and more features could be added over time, and that's the scalability aspect of it. But from the users, I mean, I know it looks very complex, and it is complex. I do agree. But from the user's point of view, there is zero management. So when you subscribe, you subscribe. You don't need it. You just don't need it. Simple as that. So there is no management from your point of view. You do not have controls over the underlying hardware or the software. There is some control depending on what you ask for. There is some control, but you don't really have direct control over the cloud provider. So that we got to make that very clear. So it's not like it's not like an on-site server, right? So you don't have control over that. You can manage your own cloud resources as an end user, but that's a limitation to that. Okay, but you can't manage the underlying services. The cloud provides for self-management. For example, it can automatically migrate virtual machines if doing so improves efficiency. So the cloud can decide on your behalf which virtual machines need to be migrated. But trust me, you won't even realize it's done that. So all of this happens flawlessly. So it's not something for you to be concerned about. What happens behind the scenes is not something you got to be concerned about. So this is the final slide. This slide summarizes what we already know about what we have learned so far about cloud. It's very theoretical so far. That's fine. We know that there are three main delivery models which we have covered last week. Which we have touched upon last week. We also know there are different types of cloud environments. There's public cloud, private cloud, etc. We have discussed the properties of a cloud, including its distributed nature, which are managed automatically. And of course, you all know about virtualization of resources, which is one of the most important principles that make the subscription-based model efficient. So I think we'll stop with that. Obviously, if you have any questions, please ask us in the online tutorial or the face-to-face support sessions. Thank you very much.